Hello friends, in our previous discussion we attempted to understand what a tensor is, or when we say that this particular quantity is a tensor or this particular parameter is a tensor, what it essentially means. So that is essentially what we try to understand or try to give a generalized understanding, again a generalized understanding in our previous discussion. For that we started off with what we refer to as the Kronecker delta. This Kronecker delta has a specific feature, that is the value assumed by it is either 1 or 0 depending on the nature of the indices. So there are only two possibilities for particularly when you consider the Kronecker delta or the description of it. When I say the nature of the indices, there are two possible nature the Kronecker delta considers. One is the identical nature between the two indices and the non-identical nature between the two indices. When the two indices are non-identical, the value assumed by the Kronecker delta is 0. When they are identical, the value assumed by it is 1. Now, this is rather a specific form of, or the Kronecker delta can rather be viewed as a specific form of a tensor, because again the value assumed by this delta, it can be viewed as a form of a tensor, a specific form of a tensor, because the value assumed by this particular quantity, this particular parameter, is rather dependent on the nature of the indices. Now, this Kronecker delta, the different values that this Kronecker delta can assume, can elegantly be represented, or it can be elegantly written as all the values that the Kronecker delta can assume can elegantly be represented in the form of a matrix. And when you are considering or assigning the definite values to I and j, both I and j in the setting that we have considered, in the context that we have been looking into, they indicate the coordinates of the coordinate system. So for three-dimensional coordinate system, they can assume values 1, 2 and 3. So therefore there are 9 possible ways or 9 possible combinations that we can arrive at when you consider the values 1, 2 and 3 that ij can assume. And in that sense, it is possible for us to then write down all the combinations of I and j in the form, or elegantly in the form of a matrix. And when we write it down, it will be of this forms: delta 1 1, delta 1 2 and delta 1 3, and so on and so forth. Now when we say that the value of this delta depends on the nature of the indices, so the diagonal elements in this case will have identical indices, so those diagonal elements will assume the value of 1. On the non-diagonal elements, they have non-identical indices, so they assume the value of 0. So what you will end up having is, you will end up having a unit matrix. So this is rather a representation of all the values the delta or Kronecker delta can assume. So ideally it can also be written as all the possible values the Kronecker delta can assume, or all the possible combinations of A and J associated with the Kronecker delta can be written as delta 1 1, delta 1 2, delta 1 3, delta 2 1, and so on and so forth, as a set of possible combination of the indices associated with the Kronecker delta. So you can write it as a set of numbers. But given the nature of the indices, given that we have two indices, they specifically vary from 1, 2 and 3, so vary between 1, 2 and 3. So it allows us to write it in or represent it in the form of a matrix. So essentially when we say Kronecker delta, it doesn't represent a matrix, it represents a specific value that depends on these two indices. But since these I and j, they have a specific value, they assume a specific value that range between 1, 2 and 3, or that range between 1 and 3, and both I and j assume these values, and therefore this allows us to elegantly represent it in the form of a matrix. So all the values that Kronecker delta can assume, so all the different combinations that are possible with respect to I and j can be accommodated in the matrix form, and therefore we are writing it in that manner. However, when you consider the Kronecker delta as a parameter individually, it is just a parameter. The value assumed by it depends on two different indices, and these indices have some physical significance associated with it. So in this case, they are the coordinates of two coordinate system. They are the coordinates of a coordinate system. Now, from these characteristic features, we can then have or extend these characteristic features to a generalized setting, and then write or cook up a parameter with associated two indices, meaning we have a parameter that is similar to that of the Kronecker delta. The similarity lies in that when the value assumed by this parameter is dependent on the nature of the I and j. the nature of the indices, the value assumed by this parameter would vary. So this can also be written as Aij. So depending on what the values I and j assume, the correspondingly the value of the Aij would vary. So therefore, as a quantity, as a parameter, value assumed by this parameter depends on the indices, and these indices have a significance associated with this. Again, in this case, it is a axis of the coordinate system. So what we can understand, the way we can understand tensor is, tensor can be treated as an extension of a vector, and in towards the end of today's lecture you will also understand how vector is a form of a tensor. But now we can, for our understanding, we can say tensor is rather an extension of a vector. In order to describe a vector, in order to vector, when we define it, we say vector is a quantity that varies with the direction. It has a magnitude, and the magnitude of that vector, it varies with the direction. Now that, so when you have a vector that is pointing at a direction, you can project it onto other directions as well. So therefore, the vector has a magnitude associated with it, and it varies with the direction. Now, in this case, the tensor that we are looking into, so this tensor is dependent on two indices. So this particular tensor, the magnitude of this particular tensor is now, instead of being governed by one direction, it can be stated that it is being governed by two different directions. So it is being governed by two different coordinate axes. So therefore, depending on the values assumed by the indices, the magnitude that is assumed by the magnitude of this particular tensor, the generalized tensor Aij, would vary. Now, similar to the way of representing it. So depending on the values I and j assumed. So the I and j, since we are restricting ourselves to a three-dimensional system, so the value of I and j could only range between 1, 2 and 3. So they could, so these values, they range between 1, 2 and 3. So therefore, all the possible combinations of or all the possible values I, this particular tensor can assume, can be written as A11, A12 and so on and so forth, and ultimately leading to A33. So all the possible values this particular tensor can assume when we are restricting ourselves to a three-dimensional system, and I and j can then assume only values 1, 2 and 3. So all the values that this particular tensor can assume can be represented as a set of numbers. Now, owing to this particular combination, so we are restricting ourselves, so owing to this particular way of assigning these indices, since we are assigning these indices through the coordinate systems and the three-dimensional coordinate system, it is possible for us to rather write it in the form of a matrix. And again, this can be written as, as a matrix, this can be written as A11, A12, A13, and this will be our 2, 2 will be our diagonal elements, and these will be our non-diagonal elements, and these will be 2, 1, 3, 1 and so on and so forth. So what essentially we do when we say, or when we write a tensor in the form of a matrix, we are considering all the possible values that the tensor can assume, provided we have already specified the nature of our indices. So once we have already specified, once we have already provided a specific definition to the indices that dictate the value of the tensor, then it allows us to rather express all the possible combination or all the possible combination of these different indices. So meaning all the possible values this particular tensor can assume, and since we are restricting ourselves to the 3 dimension, it is possible for us to write it in the form of this particular matrix. So once we write it down in a generalized manner, by looking at these different descriptions, we can come up with the idea that this can elegantly be represented in the form of a matrix. This can easily be represented in the form of a matrix, because here when we have such a description, this description here is rather just a set of numbers. But when we represent it in the form of a matrix, again without making much change, when we represent it in the form of matrix and also assign the specific meaning to each of these indices, meaning the I represents the row and the j represents the column. When we assign that, then there are several further operations that we can do if we represent it in the form of a matrix, if we move away from this description as a set of numbers, as a set. So even though the way that comes up to our mind when we think about the different combinations of the indices or the different values of this tensor, the rather straightforward way would be to write it as a form of a set. But when you look closely and when we are able to write it in the form of a matrix and assign specific meaning to the order of these indices, which we looked in our previous lecture, then it is possible for us to perform certain operation to this matrix here. So that is the reason why we move from rather just writing down all the possible combinations of I and j and all the possible values that A can assume, the tensor A can assume, just writing it down as a set, and then instead of writing it down as a set, the reason for us to translating it into a matrix is because this will allow us for further operations, further numerical operations. And when we do that, when we translate it into the form of a matrix, in addition to the physical significance of I and j, there is also a significance associated with the order in which we write our I and j. We saw that when we consider the transpose of this I and j, the transpose of this I and j will be the reversed order of the indices. So I and j, if is the original order, and when we take the transpose of it, then we can write the transpose by reversing the order of the indices. So now let us consider the relevance of, or let us consider the quantities, the parameters in the material research or in our materials or metallurgical domain wherein these tensors play a critical role. So like in the previous lecture, we just touched upon the stress as being a tensor. Stress being a tensor is something that we touched upon. We will, in this lecture, we will look closely and we will try to understand the relevance of tensor, the need for using a tensor in the materials research. Now, in order to do that, let us have a quick recap on how we describe the stress, or what are the components we need to describe a stress in a real life situation. Now, supposing if I am imposing a uniaxial tensile load to a material, let us assume as a single crystal, and I am imposing a uniaxial tensile load to this plane here. So the stress associated with this plane here, when I am imposing a uniaxial tensile load of P, the stress associated with this plane here can be represented as P by A. Now on the other hand, when you consider a sample that is made up of metals or an alloy, and when I say it is made up of metal or an alloy, it means we have rather regular arrangement of the atoms, and when we have the regular arrangement, long range regular arrangement of the atom, it is possible for us to rather describe definite planes using Miller indices. And now this could be a specific plane. However, there will be also another plane that experiences this stress owing to the uniaxial tensile load that we impose. So when you consider the crystalline material, it is possible for us to describe several planes based on the Miller indices. And so when you describe a plane that is perpendicular to the loading direction, there will also be a plane that is not perpendicular but rather inclined to the loading direction. Now, when we want to describe the stress associated with the stress that inclined plane rather experiences, we need to rather dissociate the imposed stress into components of stress. So we are imposing a load P, and this load translates into a stress on that acts perpendicular to the loading direction, on the plane perpendicular to the loading direction, and that is rather quantified by taking the ratio of the load with respect to the cross-sectional area. Now we are interested in describing the mechanical condition experienced by an inclined plane. So for that we need to understand. So in order to describe the mechanical condition we are experienced by an inclined plane. So we are interested in the inclined plane, and when we want to describe the mechanical condition experienced by the inclined plane, then we want to consider the components of stresses. So the components of stresses under uniaxial tensile loading comprises of under uniaxial tensile loading, when you want to dissociate the imposed stress into its components, it comprises of three different components. So one is under a normal stress that acts perpendicular to the plane that we are interested in. The other is two shear stresses that acts on the surface of the desired plane. So we are focusing on an inclined plane, and in that inclined plane we want to describe the mechanical condition that we are imposing. Now the stress, when we are talking in the context of with reference to that of the inclined plane, cannot be described using just one value, one scalar value. We cannot do it. We have to dissociate into its components. So when we dissociate it, then in order to describe the mechanical condition experienced by the red plane here, the inclined plane, then we need to consider three components, one normal stress and two shear components. Now when we want to have a generalized understanding of the mechanical behavior, then or the mechanical condition, when we want to impose a generalized, or when you want to talk about a generalized mechanical condition, then we can start with the triaxial loading condition. The triaxial loading condition, we can start off with the triaxial loading condition because this will give us a generalized description, and from this generalized description we can rather deduce or we can derive our specific cases. So here we are considering a uniaxial tensile loading, and for the uniaxial tensile loading we see that when our plane is inclined we need three components of stress to describe the mechanical condition experienced by the plane. Now when we want to have a generalized understanding, then we have to consider the most complicated case, or most rather a case that includes all the components, and when we have such a case, from that case we can reduce to our, from that understanding we can rather extract the case for our specific instance. So for that we can start by considering, we can move away from the uniaxial tensile load to triaxial tensile loading. For uniaxial tensile load we need three components of stresses to describe the mechanical condition experienced by the inclined plane. So therefore for triaxial tensile loading we need 9 components of stress to describe the mechanical condition experienced by an inclined plane. Uniaxial inclined plane, 3 components of stress. So triaxial inclined plane, you need 9 components of stress. Now this 9 component of stress, we have it is rather graphically it can be represented by considering an element in this inclined plane. So if you consider a small element in this inclined plane, and this inclined plane now is experiencing a triaxial tensile load. So it is experiencing a triaxial tensile load, and these 9 components of stresses that are required. So again we are trying to describe the mechanical condition experienced by the inclined plane, so it requires 9 components, and this 9 components can be graphically represented by considering an element within the inclined plane, and this element, since we are considering a 3-dimensional sample, and this element will be of the 3-dimensional form, and we are considering a 3-dimensional sample that is experiencing triaxial loading. So therefore in order to describe the mechanical condition in the inclined plane, 9 components of stress, this 9 components of stress will be of this form. They can be represented in this form, wherein we have the normal stress that is acting perpendicular to a plane, and the shear components of stress that is acting on the plane. So normal stress that is acting perpendicular to the plane, and the shear components of stress that is acting along the plane. The same way, the normal stress that is acting perpendicular to the plane, and the shear stress that is acting along the plane. So now if we assume the coordinate system to be x, y and z, so this stress is often referred to as, so this stress will be normal stress that is acting along the z direction, and this stress is the shear components of the stresses. So we have the shear components of the stresses that are acting along the planes, and we have the normal components of the stresses. The normal component of the stresses can be named rather AZD, so we have the normal component x, the normal component y. Now when you consider the shear components of the stresses, we need 2 indices because they are acting along a plane and they are pointing in a specific direction. So these, when you consider these shear components, so one that are in red, these shear components, they need 2 indices because they are acting along a plane and in a specific direction. Now we can rather begin by describing each of these planes that we have considered. Again, this if you have a good memory, if you have understood this in your previous courses, then this would be rather a recap of what you have already understood, but given the chance that you have rather have forgotten it, now maybe we are spending some time to understand why we need, or why it is required for us to use tensor to describe the stresses. So now these shear components of stress, they are acting in a specific plane and they are not uniformly acting, they vary along the direction. So if we are, so this plane is the z plane as it cuts the z axis. So these 2 stresses, the first rather index of these 2 stresses will be z because they are acting along the z plane, and similarly the first index of these 2 stresses will be x because they are acting along the z plane, and the first index of these 2 stresses will be y because they are acting along the y plane. So the shear components of the stress, they are acting on the surface of the plane, but they vary with the direction. So we need 2 indices. One index, the first index, it describes the plane on which the shear component of the stress is acting. Now The second index will describe the direction. So in this case, the second index will be y because it is acting along the y direction. In this case, the second index will be x because it is acting along the x direction. In the same way, in this case, the second index will be z as it is acting along the z direction. In this case, it is y as it is acting along the y direction. So in this case, the second index will be z as it is acting along the z axis, and in this case it will be x as it is acting along the x axis. Now when we combine all these different components of stresses, so that is sigma x, tau xz, tau xy, sigma y, tau yz, tau yx, sigma z, tau zx, tau zy. What we have essentially done is we have written down all the possible values, the stress that could assume depending on the indices. So what we have done is we have shown that for a generalized case of triaxial loading, when we focus on a plane that is inclined, we need 9 different components of stresses to describe the mechanical condition experienced by the plane. And these 9 different components of the stresses, they depend on the plane and the direction. So meaning they need to assume a specific value. We need to assign 2 different indices to this parameter, to this quantity, and only then they will assume a different value. So when you give such a description to the stress, then all possible combination of the indices and all possible values the stress can assume, these 9 different components can be written in this manner. Now it is possible for us to write these normal stresses as xx and rewrite the whole set of values these stresses can assume. So we can rewrite all these different 9 components by replacing the sigma x with tau xx. And when we do that, this allows us, when we replace the normal stresses with tau xx, because in any case they are going to assume, because when we represent it in the form of a matrix, it will assume a diagonal limit. So to be consistent, we have translated it to tau xx, and now again we still have the set of 9 different components the stress is going to assume depending on which plane and which direction we are considering. And once we have written it like this, it becomes possible for us to represent it in the form of a matrix, and this can be written as, so the stress can be written as this matrix here. And what this matrix indicates is the different values the stress can assume depending on the indices, depending on the plane and the direction value which we are focusing. So far we have not expressed, or we have not included the term tensor here. We have just been talking in terms of purely from the materials perspective. We are talking about stress, we are talking about a generalized representation of a stress that is acting and we are focusing on an inclined plane within the material. And we have seen that when you are considering a generalized case involving triaxial tensile loading, and when we are focusing on an inclined plane, then we need to describe the mechanical condition experienced by this inclined plane. We need 9 components of the stress, and these 9 components of the stress are represented in this manner. So far, no concept, or we have not even talked, or we have not touched upon the tensors as of yet. So what essentially then we have is, so when we start from purely a materials perspective, and now we are trying to define the quantity of stress for a triaxial loading condition, that is, and focusing on an inclined plane, we need 9 different components of stresses to describe the mechanical condition. So these 9 different components of the stresses, owing to their nature, owing to the way we have written it down, the way they vary, these indices vary, we have written it down in the form of a matrix. And again, if we replace x with 1, y with 2, z with 3, we will be able to write the stress as a form of a conventional matrix, wherein the first index governs, or it takes care of the row, and the second index rather it is associated with, rather the first index it takes care of, it stays constant, or it indicates the row, and the second index rather it represents the column. So what essentially we have so far been doing is, we have just been representing a quantity, a stress under triaxial tensile loading when the triaxial and focusing on an inclined plane. Now, the value of the stress depends on the nature of the indices. The value of the stress depends on the value that is assigned to the indices. So therefore, when you consider a specific combination of the indices, the corresponding value of the stress will vary. So therefore, when I say the stress Ij is a tensor, it fulfills all the fundamental criteria that we often associated with a tensor. That is, a tensor, at least in this case, when it is associated with two indices, the value assumed by it would vary. And when you consider all the possible combinations of these index that describe or that dictate the value assumed by the tensor, it can be rather represented in the form of a matrix, and we were able to do so for the stress. So essentially, then stress is not a scalar, but rather in the context, in the generalized stressing setting of a triaxial tensile loading, and particularly when our focus is on the inclined plane, the comprehensive way of describing a stress would be in the form of a tensor. And the reason we should represent the stress as a tensor is because this stress is dependent on two indices. It is dependent on, at least when you consider the physical meaning of it, it depends on the plane along which it is acting and the direction along which it is acting. So therefore, we need to have two indices to represent this stress, to represent the different components of the stress. So depending on the values, depending on the nature of the indices, the particular stress experienced would vary. So therefore, the stress is rather a tensor, and it varies with the nature of the indices, the value assumed by these indices. Now, similar to that of the stress, it is also possible for us to show that the strain is also a tensor. So the tensor nature of the stress comes from our focus, again, because we want to have a generalized understanding, we want to have a generalized description of the stress. We consider a generalized loading condition. The generalized loading condition is a triaxial loading condition, and we have considered a plane that is rather inclined. Now, from this tensor representation, we can impose the specific cases of uniaxial tensile loading, and correspondingly the matrix here would vary. So correspondingly, certain values here would assume, so certain entities here would assume the value of 0. So when you focus on the uniaxial tensile loading alone, certain values here would assume the value of 0. And again, depending on which plane you are focusing, the values, certain entities here would, again as an example, certain entities would assume the value of 0, and only there will be few non-zero elements, purely an example. Okay. So what essentially then we have here is, when we say that stress is a tensor, the stress can be represented in the form of a tensor, or stress in a generalized sense is a tensor, then we are giving again a generalized description to it. So based from this generalized description, we can arrive at the corresponding, the desired expression for the tensor. So that desired expression rather for the stress. So stress as a tensor is a generalized way of representing it. So generalized way, we are considering the triaxial loading condition in often for an inclined plane. So this is the generalized setting that we can consider, and for that generalized setting, the stress is expressed as a tensor. And if we want to narrow it down to a specific case of uniaxial tensile loading, uniaxial tensile load that is acting on a perpendicular plane, then all these other entities will turn out to be 0, and only one non-zero entity would be present. So what essentially then we have is, from the generalized expression, we have now arrived at a specific representation for the stress. So the stress as a tensor would help us describe the mechanical condition in a most generalized way. So irrespective of which plane we are considering, irrespective of which nature of stress or which nature of loading condition we are considering, when we describe stress as a tensor, we are expressing it in a most generalized way. So that is the reason why, when we are considering theoretical studies, when we are considering a theoretical model, we often tend to build the theoretical model from a generalized standpoint, so that this generalized theoretical model can be reduced to specific instances. And that is the reason why, whenever in a theoretical model the stress is involved, it is represented in the form of a tensor. So in all theoretical models where the stress is involved, be it the stress to introduce some elastic strain or the stress to introduce a plastic strain, wherever the stress is involved in a theoretical model. In a materials research, the stress is expressed as a vector, rather a tensor, primarily because tensorial representation of the stress is the most generalized one, and from that tensorial representation, from that tensor representation, we will be rather able to deduce the specific cases of uniaxial tensile loading for a plane that is perpendicular to the loading direction. So therefore, whenever you come across any article that includes stress in its theoretical model, it will be in the form of a tensor, and this is the reason why. So this stems from the components of stresses that is required to provide a comprehensive understanding, a comprehensive description for the stress, and this components of stress, they elegantly align themselves in the form of a matrix, and this component of stresses rather they are dependent on two indices, and that's the reason we have a specific shape for this matrix. That's the reason why we also have, since the tensor representation of the stress is the most generalized one for any theoretical model, since they have to start off from a generalized description, we have stresses being treated as a tensor, and from that generalized description we will be able to rather deduce to, or will be able to apply it for any specific case. Right. Now, similar to the stress, it is possible for us to rather the generalized description of the strain is also in the form of a tensor. When you want to rather give a generalized description for the strain, it will be also in the form of a tensor. So this can be understood by considering again a sample under triaxial tensile loading. We will have a sample under triaxial tensile loading. So when you consider a triaxial tensile loading of this form, so we have our x, y and z direction. So this will be our y and this will be our z direction, and all these, among all these three different directions, we are imposing our load. So we are imposing the load px, py and pz. Now when you consider strain along the direction x, so along the direction x, so the strain along the direction x can be caused by the load along x. So the first index, the strain along the direction of x, can be caused by the load along the x. So therefore, the second indices, it represents the direction of the strain, and the first indices, it indicates, or rather it's the other way around. The first index, it represents the direction of the strain, and the second index, it represents the load direction that is responsible for the strain. So the first index, it represents the direction of the strain, and the second index, it represents the load direction that is responsible for that strain. So the strain along the x direction can be due to the, or is largely due to the load that is acting along the x direction. It is also possible the strain along the x direction might also be due to the load along the y direction because of the Poisson's effect. So because of the Poisson's effect, it is also possible to have the strain along the x direction because of the strain along the y direction. So because of the strain along the, so this will be our y load and this will be our z load. Because of the strain along the y direction, it is also possible for us to have, because of the load along the y direction, it is also possible for us to have a strain along the x direction because of the Poisson's effect. In the similar way, it is also possible for us to have the strain along the x direction because of the load along the z direction, again because of the Poisson's effect. So essentially what we have is the strain along the x direction, it can be due to the load along the x direction, or it can be due to the load along the y direction, or it can be due to the load along the z direction. In the same way, the strain along the y direction, it can be due to the load along the x direction, load along the y direction and load along the z direction. In the same way, the strain along the z direction can be due to the load along the x direction, load along the y direction and the load along the z direction. So what essentially we have now is, we have considered all the possible combination of the strain. So all the possible ways the sample that is experiencing triaxial loading can deform, can strain. So we have considered, we have split the strain into three different axes, along the three different axes, and now we have seen that a strain along a particular axis will not only depend on the load along the same axis, but also the load that is acting perpendicular to that. So therefore, we need two indices to describe a specific strain. So the strain along a specific direction will not only be dependent on the the load along the same direction, but it will also be dependent on the load along the other directions as well. So therefore, we need two indices to describe the specific strain. Now, it is possible for us to replace x with 1 and y with 2 and so on and so forth, but since this strain as a parameter depends on these indices, two different indices, and since these indices have a physical meaning associated with them, so therefore the generalized representation, again this is a generalized representation, so even when you treat this as a set of numbers, these are a generalized representation, and these can be translated to a matrix of epsilon 11, epsilon 12, epsilon 13, epsilon 21, epsilon 22, epsilon 23, epsilon 31, epsilon 32, epsilon 33, where we have x is equivalent to 1 and y is equivalent to 2 and z is equivalent to 3. So what we have essentially then we have done is we have represented the different values the strain can assume depending on the indices in the form of a matrix, and this matrix representation means we have included all the possible values and we have represented it in a unique way in such that the order of the indices also have a significance. So the generalized representation of the strain, similar to that of the stress, is in the form of a vector. So we need to have a vector representation to describe generally the strain that is experienced by a material. Of course, when we rather simplify the loading condition to a uniaxial loading condition, then correspondingly the several entities in this representation will assume a value of 0, and there will be only few non-trivial entities present. However, nevertheless, the generalized representation then would require treating the strain as a tensor. So owing to this reason, purely from the material's perspective, it is possible for us to understand that the stress and strain cannot be treated just as a vector alone. We need a different representation for it, and that different representation that allows us to generally handle, in a generalized setting, to handle both stress and strain as the tensor. So when we handle the stress and strain as a tensor, it allows us rather to discuss both the tensor, both stress and strain in a generalized context. If not for the tensor representation, we have to describe the stress and strain for the specific instances or specific conditions alone, and developing a generalized model, a mathematical model for specific instances or specific mechanical condition is not that fruitful. So therefore, this tensor representation allows us to describe stress and strain as in a generalized manner, thereby allowing us to use these stress and strain for developing rather numerical models. So now we have seen the relevance of tensor representation, the relevance of this tensor quantities in the material research. At least we have considered two different parameters within the same context of mechanical behavior of materials, where tensor representation of it is highly helpful. In both these instances, stress and strain, both these allow the tensor representation allow us to treat both these in a generalized manner, thereby enabling us to use them in the theoretical models. Now let us consider, before we wind up this lecture, let us consider a few of the terminologies associated with the tensor. Now the tensors that we have so far been looking into, they comprise of, so we will start off with a generalized tensor, rather a tensor that we have rather cooked up. So this comprises of, or this depends on two different indices, and the value assumed by it vary depending on the value assumed by these indices. Now this tensor, we have assigned that these indices, they indicate the axis of the coordinate system, and since we have restricted ourselves to three-dimensional coordinate systems, so there are three values each of these index can assume. So when we represent this in the form of a matrix, we will have 9 different entities. So what essentially we have is, we have a tensor that is described using two different index and two different indices, and these two different indices, they have a physical meaning, they are attribute to the axis of the coordinate system, and since we have we are restricting ourselves to a three-dimensional system, so the values assumed by them are 3. So therefore the total number of values that are possible for this particular tensor is 9. The way we have arrived at this 9 is because it is possible for us to write it down in the form of a matrix, and when we count it, it is a 3 cross 3 matrix and 9. But one other way of understanding this would be, since it depends on the combinations of I and j. So we have I assuming 3 values and j assuming 3 values, and it depends on the combination of I and j. The number of values associated with, the number of entries associated with this particular tensor is often, it can be written as 3 power 2. So 2, it is rather the different combinations, or it rather indicates the number of indices that are present, indices that are present and that assume the value between 1, 2 and 3, and 3 is the number of values that each index can assume. So the total number of entries associated with the total number of entries, or the total number of all the total values that this particular tensor can assume is 3 square, and that ultimately leads to 9 entries. So what essentially we have is, this form of a tensor is referred to as the second order tensor, because we need 2 different indices. This tensor is dependent on 2, or when you want to describe this tensor, you need 2 different indices to describe it, and the value assigned by this tensor depends on the value assigned to these indices, and the number of entries that are associated with. When you write down the number of possible values, the second order tensor can assume it will have 9 entries, and this can be derived by, or the 9 entries, we achieve the 9 entries by raising the number of values assumed by I and j, the indices, to the power of the order. Now if we restrict ourselves to 2-dimensional case, from 3-dimensional, if we restrict ourselves to 2-dimensional, then I and j will assume the value of just 1 and 2. Now in that case, the number of entities that are required to describe the tensor I and j, so the total number of entities that are possible that are required to describe I and j would be, here we just have 2 possibilities of I and j, so 2 to the power of 2, therefore we will have 4 entries. So the matrix will be 2 cross 2 matrix, and the possible values, this particular second order tensor in 2 dimension, the second order tensor in 2 dimension will be, it can assume 4 different indices. So the second order tensor in 3 dimension, 9 entries, the second order tensor in 2 dimension is 4 entries, so it is 2 square, and here it is 3 square. Now we have looked into vector spaces that have more than 3 dimension, and that is, it is possible there for us to have rather k dimensions. So in those instances, when we have a tensor ij, aij in a vector space, the number of possible values this particular tensor, this particular quantity can assume will be k square, and the size of the matrix will be k cross k, and the number of entries this particular tensor in a vector space of k dimension can assume is k square, and this is what we refer to as the second order tensor. Now when you consider the third order tensor, the expression for identifying when you consider the third order tensor in 3 dimension, the expression for identifying the number of entities that are required to describe the given tensor can be estimated using the same approach that we have adopted here. So the third order tensor can be expressed, it is usually expressed using I, j and k, and we will let us focus or restrict ourselves to 3 dimension. So this I, j and k will assume the values between 1, 2 and 3. So the total number of entries that are possible for a third order tensor, so it will be 3 to the power of 3, so totally it will be 27 entries. Now if you restrict ourselves to 2 dimension, I, j and k will assume a value between 1 and 2 only, so therefore it will be rather 2 to the power of 3, ultimately 8 entries is what we require to provide a generalized description of the third order tensor. Now again, when you consider third order tensor and when you want to write it in the form of a matrix, we need to have a 3-dimensional matrix to represent it. So there are other ways to bypass it that we will look into the next lecture. But let us now, before winding this lecture up, let us consider what is a first order tensor. So when you consider a first order 3-dimensional tensor, so it can be represented in the form of ai, So we will have only this particular tensor is dependent on only one index, and this index will vary from 1, 2 and 3. And when you consider the matrix representation of it, it will be 1 cross 3 matrix, because the number of entries for the first order tensor will be 3 to the power 1. So whatever order that we are considering, see, supposing if I am considering an n-order tensor, the n will assume the exponent. When you want to estimate the number of components associated with the tensor, so this will assume the exponent, and the nature of the system that we are considering, be it 3-dimension, 2-dimension, or any dimension, the dimension will assume the lower value. So the k, if you are considering k dimension and an nth order vector, so k power n is the number of entries that is required to describe that particular tensor. So you have an nth order tensor with k dimension, k power n is the number of entries that are associated that we need to describe that particular tensor. Now when you focus on, get back to the first order tensor, so we have the order is 1, so it assumes the exponent role, and we have its 3 dimensions, so 3 power 1. So essentially if we write it down, we can write it down as A1, A2 and A3. So this is how generally we write it out. We write this particular matrix as, and this is nothing but rather a representation of the vector, the column representation of the vector. This is something that we have looked into. This is nothing but the column representation of the vector. So therefore the first order tensor is nothing but a vector. So the first order tensor is nothing but a vector, and when you consider a tensor which that is dependent on only one index, it is nothing but a quantity that is dependent on one direction, so which is nothing but a vector. And when you write it down in the form of a matrix, you will write it in this form, which is nothing but the column representation of a vector. So first order tensor is a vector. And in the same way, when you consider a 0th order tensor, so when you consider a 0th order tensor, what you essentially have is a tensor that is not dependent on any index, so that means it's a scalar. So a 0th order tensor is a scalar, first order tensor is a vector, and all the other order tensors are the order tensors. So everything can be represented in the form of a tensor. So generalized description, again it comes back to the way we introduce the tensor. So the tensor gives us a generalized way of describing any quantity. If the quantity is a scalar, we can represent it as a 0th order tensor. If it is a vector, first order tensor, and if it is of any other, when it is of any other higher orders, we can represent it as a corresponding order tensor. So with this we will wind the present lecture up, and we will consider look into the further ways of writing down these tensors in the subsequent lecture. Goodbye.